Currently, although academic discussions about the origin of the Earth are still filled with controversy, some common viewpoints have formed. However, when it comes to the origins of the Sun and the solar system, humanity's speculations and research methods are relatively limited, as we have not directly observed the formation process of a star. Yet, with the progress in archaeology and the interpretation of ancient cuneiform texts, we were surprised to find that the ancient Sumerian civilization had recorded insights about the origins of the solar system on clay tablets thousands of years ago. According to these ancient documents, the solar system was initially composed of three major celestial bodies: the Sun, called Apsu, Mercury, called Mummu, and a body named Tiamat. The Sumerians viewed Tiamat as the source of life. The story mentions that there were dense primordial waters between Apsu and Tiamat. In these waters, other celestial bodies were born, representing what we know today as Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. These bodies orbit the Sun in a counterclockwise direction. Beyond these planets, there is another massive body named Marduk by the Sumerians. Marduk's orbit was exceptionally wide, taking 1,000 years to approach Earth. Marduk was the only body that revolved clockwise, and, when its orbit neared Apsu, it overlapped with Tiamat's orbit, making a collision very likely. To avoid a collision with Marduk, Tiamat, having its own consciousness, created a satellite named Kingu to protect itself, which was exceptionally sturdy. Despite Tiamat's protective measures, it eventually collided directly with Marduk. The collision split Tiamat into two, with one relatively intact piece carrying the satellite Kingu falling into the region between Venus and Mars, becoming the Earth as we know it today. The other part became fragmented, forming a ring around Mars' exterior, which became the boundary between the inner and outer solar system. Marduk itself was almost unaffected and continued to orbit Apsu, the Sun, with a period of 3,600 years. This star is considered the home of the gods, namely Nibiru. Initially, when people learned about the Sumerian civilization's description of the solar system, many found it hard to believe. This skepticism was understandable. It wasn't until 1981 that humans discovered about 10,000 asteroids between Mars and Jupiter, and around the same time, the concept of the asteroid belt was established. As technology advanced, the existence of the asteroid belt was confirmed, with scientists estimating at least 500,000 observable asteroids within this region. The deeper understanding of the solar system has made the ancient information carved on stone tablets thousands of years ago profoundly impactful on modern people. Indeed, the asteroid belt located between Mars and Jupiter resembles a bracelet, serving not only as the boundary of the inner and outer solar system, but also astonishingly matching the descriptions found in Sumerian texts. However, there's still no consensus in the academic world about the existence of Nibiru, called Marduk. In the process of observing the solar system, phenomena suggesting the presence of unknown celestial bodies are often encountered. For example, when observing Halley's Comet, scientists noticed its orbit seemed to be disturbed by an unidentified force, potentially pointing to the unseen Nibiru. But without direct observation, is there evidence to prove its existence? A mysterious event in 2008 sparked speculation that Nibiru might have been observed but intentionally hidden, particularly from August to October 2008, when signs of an unknown celestial body near Saturn were supposed to be observable. Astronomical software like Microsoft Worldwide Telescope and Google Sky showed malfunctions in critical areas, leading to a patch being obscured and missing the optimal observation period until the system was restored after the window had passed. Google and Microsoft claimed these were due to system errors, but astronomy enthusiasts noted that observation data related to the obscured area were deleted during that time. Normally, such system malfunctions should not affect the precision instruments collecting astronomical data. This implies that, although we couldn't see these data, it doesn't mean the instruments didn't record relevant observation information. This mysterious phenomenon has led to widespread speculation about whether certain individuals or groups, for some reason, do not want the public to know about certain astronomical events. When discussing the topic of Nibiru, our stance is that human technological advancement isn't advanced enough yet for us to engage in deeper space exploration. Considering the vastness of the solar system, our understanding remains limited. Since the discovery of Neptune, It has only made approximately one orbit around the sun. As for Nibiru, which is said to return every 3,600 years, finding it poses a significant challenge. If we assume Nibiru returned in 2008, its previous return would have been around 1592 BC, a period that coincides with the Middle Kingdom of ancient Egypt, the early city-state era of ancient Greece, and the Shang Dynasty in China. We might find clues about Nibiru in the records left by these civilizations. Moving on to our sun, known as Apsu. We're often told that the sun is a massive ball of fire undergoing constant nuclear fusion, with almost all of Earth's heat coming from this process. This is widely accepted by most people. However, the concept of the sun's nuclear fusion is actually a theoretical assumption, not a fact without controversy. In 2018, NASA launched the Parker Solar Probe with the mission of closely observing the sun's outer corona. Why would the United States, a leader in technology, spend $1.5 billion to explore the sun if we already fully understood it? Therefore, everyone, please be patient. By 2025, many secrets about the sun will be revealed. With the advancement of technology, humans may indeed be able to approach or even land on the sun one day. The belief in the sun's nuclear fusion is mainly based on 2 points. First, the analysis of the sun's spectrum shows the absence of lines for 2 elements, hydrogen and helium, leading people to deduce that nuclear fusion of these elements occurs in the sun. Secondly, nuclear fusion is the only process known to generate energy on a scale comparable to the sun's, making it the primary method for the sun's energy production. However, since humans have never been able to observe the sun up close, this idea, despite wide academic acceptance, remains just a hypothesis, not a proven fact. As we delve deeper into our study of the sun, the widely accepted theory of solar nuclear fusion is being re-evaluated. A key question arises from observations of the sun's surface temperature. Through the analysis of the sun's spectrum, scientists estimate its surface temperature to be about 6,000 degrees Celsius, similar to the temperature at Earth's core, which is far below the millions of degrees Celsius needed for nuclear fusion reactions. If a mere 6,000 degrees Celsius could support nuclear fusion, then Earth's core would have exploded long ago, and we wouldn't be able to survive. Scientists explain that although the sun's surface temperature is low, the actual nuclear fusion reactions occur inside the sun, where temperatures reach up to 15 million degrees Celsius, and the pressure is about 300 billion atmospheres, meeting the necessary conditions for nuclear fusion. However, meeting these conditions alone doesn't fully explain the phenomenon, because in a vacuum, heat cannot be conducted as it is in an atmosphere. Also, according to our understanding of nuclear fusion, objects closer to the center of the reaction should receive more energy and therefore have higher temperatures. However, Mercury serves as a counterexample. It is about 57.91 million kilometers, or 0.38 astronomical units, from the Sun, a proximity that should, in theory, make Mercury an extremely hot planet. But observations made by the Mariner 10 spacecraft in 1974 and 1975 revealed different facts. The findings showed that Mercury's surface temperature can reach up to 427 degrees Celsius in the sunlight during the day and drop to -173 degrees Celsius at night. Even during the day, Mercury's maximum temperature doesn't exceed Venus's surface temperature. Surprisingly, there is ice at Mercury's North Pole, with temperatures consistently around -173 degrees Celsius throughout the year. If Mercury, like Earth, has a certain thermal conductivity, its surface temperature should be extremely high due to its closeness to the Sun. So why isn't Mercury the hottest planet in the solar system? Why does it still have a cold environment with temperatures consistently around -173 degrees Celsius? These observations lead to further discussions on the Sun's energy transmission mechanism and the theory of nuclear fusion. When we talk about the temperature of the Sun, there's a puzzle we can't ignore. Even though the Sun shines brightly, its temperature doesn't seem as high as we'd expect. In other words, the process of the Sun emitting light doesn't seem to produce the heat we thought it would. This raises a question: why can the surface of Mercury reach such high temperatures? There are also some phenomena related to the Sun's nuclear fusion that are hard to explain, especially the behavior of solar flares and solar wind. The surface temperature of the sun is around 6,000 degrees Celsius, but the temperature of solar flares can easily reach tens of millions of degrees, even exceeding 100 million degrees, far above what's expected inside the sun. Usually we think if nuclear fusion inside the sun is the source of energy, then this energy should decrease as it travels to the surface of the sun, and the temperature should significantly drop. However, the exceptionally high temperature of solar flares doesn't fit this expectation. What's more shocking is that, according to calculations, a solar flare lasting a few minutes to tens of minutes can release energy equivalent to 1/10,000th of the total energy the sun emits. If these calculations are correct, then tens of thousands of solar flares could deplete the sun's energy. Given that the sun has experienced countless flares since its formation, how it replenishes this energy remains a mystery. Solar wind is another phenomenon that nuclear fusion theory struggles to explain. Solar wind consists of a high-speed stream of plasma and charged particles ejected from the sun's upper atmosphere, a phenomenon that has been constant since the sun's formation, shooting out at speeds ranging from 200 to 800 kilometers per second. Mysteriously, the speed of the solar wind doesn't seem to decrease with distance, always maintaining high velocity. Near Earth, the speed of the solar wind can stay between 350 to 450 kilometers per second, sometimes even reaching the original speed of 800 kilometers per second. In contrast, human nuclear fusion experiments on Earth show that the energy released during fusion is almost instantly expelled, producing a plasma flow similar to the solar wind. However, the speed of energy shooting outwards gradually slows down. This behavior is somewhat inconsistent with the characteristics of the solar wind, which continues to be ejected from the sun as part of its ongoing nuclear fusion process. Current observations show that the speed of solar wind at its point of origin on the sun's surface ranges from 200 to 800 kilometers per second. However, by the time it reaches the vicinity of Earth, its speed is usually within the range of 350 to 450 kilometers per second, occasionally even reaching up to 800 kilometers per second. This phenomenon is unexpected because once the solar wind leaves the sun's surface, theoretically, it should not have any further acceleration, and its speed should decrease with distance. Yet, actual observations indicate that the solar wind near Earth not only maintains its initial speed but often even accelerates, challenging our conventional understanding. There are two possible explanations for this phenomenon. One is that solar nuclear fusion under cosmic conditions might trigger an unknown mechanism that accelerates the charged particle stream. Another hypothesis is that the sun might not be undergoing nuclear fusion at all. Moreover, the glacial periods in Earth's history also pose a challenge to the theory of solar nuclear fusion. Based on our understanding of nuclear fusion reactions, once started, it should be very stable, continuously releasing energy outward. However, Earth, which relies on the sun as its primary energy source, has experienced multiple glacial periods throughout its history. It is believed that the energy exchange relationship between Earth and the sun has been maintained for billions of years, with the sun steadily providing energy to Earth, and Earth's position and conditions for receiving solar energy have not significantly changed. Yet Earth's history has seen several glacial periods, lasting from tens of thousands to millions of years. Does this imply that there was a change in the sun's energy output during the glacial periods? Research into the sun continues, and while many scientists adhere to the nuclear fusion theory, discussions on the source of the sun's energy have not ceased. If the sun does not generate its energy through nuclear fusion, what then is its source of energy? Are there any new theories to explain the production of solar energy? Indeed, there is such a theory. The plasma cosmology proposed by Hans Alfvén, the 1970 Nobel Prize winner in physics from Sweden, is one of them. This theory can explain a series of anomalies observed in the sun and offers a possible explanation for dark matter. However, this theory has not been widely accepted, partly because it does not provide an explanation for the origin of the universe.